Good day, everyone. We are the group 4 and we will going to discuss our chosen topic about functions. A functions in set theory world is simply a mapping of some or all elements from set A to some or all elements in set B. Let A and B be two sets. Then a function is a rule that assigns to every element of A one and only one element of B. We let F denote this rule and write F is to A implies B. If A is an element of A and our rule assign B is an element of B to this A, we write F of A equals to B. We say F is a function from A to B. A is the domain of F and B is the codomain. And F of A is equals to B, then B is the image of A. We have there a note that a function depends on the three things: the rule F, the domain A, and the codomain B. Change any of these and you have a different function. As you can see on the picture below, we have there a set definition, and that picture set states that the function is not one-to-one. It is because the horizontal line intersects the graph at more than one point anywhere, then the function is not one-to-one. So we have there a note that we can use pictures to show what we do not want to see in the function. So we never want to see, just like the two pictures shown below.
B is relations. Example 74. The above or pictorial example may be written as F equals 1B, 2B, 3A, 4D, and subset A times B. So a function is a relation between sets, yet G equals 1B and 1A and 3B is not a function because firstly, the image of 1 is not unique, and secondly, what are the images of 2 and 4? So functions are particular type of relation between sets.
C. Formula. Example 75. Define f of r implies r by f of x is equal to 2x cubed minus 1, or x implies 2x cubed minus 1. So f of 0 is equal to negative 1, and f of negative 1 is equal to negative 3, and f of 1 is equal to 1, and f of 2 is equals to 15, and so on. So below is the graph, which is pictorially.
Example 76. Define f n implies q by f of 1 equals to 1/2, f of n plus 1 is equals to 3, f of n plus 5 for all n greater than or equal to 1. So f of 1 is equals to 1/2. F of 2 is equal to 3 times 1/2 plus 5 is equal to 13/2. F of 3 is equals to 3 times 13/2 plus 5 equals to 49/2, and so on, and it can be shown that f of n is equal to 3 to the power minus 5 over 2 for all n greater than or equal 1.
In line with that, next will be one-to-one and onto functions. So, here's the definition. A function f a to b is one-to-one or injective if different elements of A are mapped to different elements of B. Pictorially, the definition of one-to-one means that we never want to see. As you can see, the example on the left side, which is letter A, and the other side is letter B, the 1 is pointed into letter B. Number 2 is pointed on letter B also, and number 3 is pointed into letter A. We can write out the definition using quantifiers because the definition tells as what that we never want different elements to have the same image, that is not there's A1, there's A2, f A1 is equal to f A2, and A1 is not equal to A2 is defined for all A1 not A2. F A1 is equal to F A2, and A1 is not equal to A2. Next is defined for all A1, for all A2, F A1 is equal to F A2 implies to not A1 is not equal to A2. So, you must recall the not P and Q defined as P implies not Q. Lastly, it is defined as for all A1, for all A2, F A1 is equal to F A2 implies with A1 is equal to A2. Next, to check if a function is one-to-one, we need to show that the conditional statement is f A1 is equal to f A2 implies with A1 is equal to A2 is true for all elements A1 and A2 from A. If we use the method of proof CP, it suffices to assume of f A1 is equal to f A2 and try to deduce A1 is equal to A2.
Example 77. The first picture figures out that the function is 1 but not on 2. In the second picture, figures out that the function is 1-to-1 and on 2. So, f1 is to A implies B is a different function from f1 is to A implies B, even though the rule is the same. In the third picture, it turns out that the function is not 1-to-1 because 3 is not equal to 4, but f2 of 3 is equal to f2 of 4, yet the function is on 2, so f1.
Let's proceed to the proof of 4. We see the negative 1 unequal 1, but function negative 1 equals 1 equals function 1. So the function is not 1 negative 1. Now, given negative 1, there does not exist y element r such that function y equals negative 1 ia. Y squared equals negative 1 has no solution in R. So, the function is not onto. The function R implies Rx implies 2x negative 1 over 3 is 1 negative 1 and 2.
Proof 5. Assume f and x equals to f and y. So, 2x minus 1 is equals to 3. 2y minus 1 is equals to 3. So, write times and add 3 because the result is 3. So, 2x minus 1 equals 2y minus 1. The result is 1 minus 1. So, positive 1, 2x is equals to 2y. X in 1 half is equals to x and y. Thus f and x equals f and y implies x equals y. Hence, the function is 1 minus 1. Now, given any x, they are, we need to find y such that f maps y onto x, that is f and y is equals to x I e. So 2y minus 1 over 3 simply rearrange as 2y minus 1 over 3 is equals to x. x3 2y minus 1 is equals 3r plus 1. 2y equals 3x plus 1. X in 1/2. Y is equals to 3x plus 1 over 2. So choose y equals 3x plus 1 over 2 as this works for any x. The function is onto. Definition: we say that f, a, and b is a bijection or a 1-in-1 correspondence if it is but 1 minus 1 and onto. So by example 77 and 5, we say that f r and r 2x minus 1 over 2 is a bijection.